All right, hello class. I'm going to keep this really short and sweet, but hopefully you guys enjoyed your break. I apologize for the videos before break that apparently had really bad sound quality. So I tested this out. Hopefully this works a little bit better. So I got my board here. I'm just going to draw. So today, I'm going to start doing work and energy a little bit. And this stuff isn't going to be on the semester exam, but it is going to be our next chapter. So it's kind of a little bit of an intro in this awkward 6 days before you guys have before exams. So at the beginning of class today, you guys watched two short videos, the Professor Dave Explains videos that introduce the topics of work, energy, as well as kinetic energy, potential energy. I'm going to kind of touch on that a little bit more right now, but your assignment for today is pretty straightforward. It's just an article. I'm going to try to connect this next chapter to our article. Okay, so the first thing we learned is, of course, work. Work is kind of what we call the usage of energy. It's a transfer of energy. So I guess maybe we should put up there energy as well. Okay, so energy, as already defined, is the ability to do work. Okay, work can be pretty much anything. Okay, work is moving things, transferring things, speeding something up, slowing something down. It's making things happen. Okay, changing things, moving things, crushing things, killing things, destroying things. Having that ability is the energy. Now we're going to talk about all different types of energy at some point in this chapter, and the different types of energy are just basically just why things are able to do work, why things has the ability to move things, crush things, kill things, do whatever it is. So work is, we can define that as a transfer of energy. When you do work on something, you're taking energy from that you have stored inside of you and moving it to something else. So say when I lift something, I have chemical potential energy stored in my body. And I'm lifting something up for the ground, say up to a high shelf, to increase its energy in some shape, way, or form. If we're increasing its height, we're increasing its gravitational potential energy. Now that it's up on that shelf, it could potentially fall off and crush something or what have you. Or I could use chemical potential energy stored in my body to grab a baseball and throw that baseball. And then I'm giving that baseball moving energy, what we call kinetic energy. Those two are the two main ones that we're going to talk about, is gravitational potential energy and kinetic energy. So gravitational potential energy, which is referred to as PE, kinetic energy, KE. When something has this type of energy, it's able to do work because of its position, because of its raised some height. Okay, so gravitational potential energy has to do with height. Kinetic energy has to do with motion. Okay, things with kinetic energy are able to do work, are able to do things because by virtue of its motion. Objects with gravitational potential energy are able to move things, or able to do things because of its position, raised above the ground, and that gravity could potentially act on it. Okay, so we'll write up in here for work, using energy. We can define work a few different ways. We could also say when a force makes an object move. We'll talk more about that second one yesterday. You could also describe it as a transfer of energy. Like I said before, when I throw a ball, okay, I am taking energy stored in me and I'm giving it to that ball. Okay, that's energy that I have less. Every time you give something energy, that's that much less energy that's in your body. So that kinetic energy that baseball has, that was part of my pool of energy that I have in my body, called, we usually call that calories. That's what a calorie is. On a diet or whatever, you're always concerned with how many calories are in this or that, but calories is just a unit of energy. The unit we typically like to use in physics class is the joule. But both are just different units. So, I think they say usually most people have all the nutritional facts on the labels of food or whatever are based on a 2,000 calorie a day diet. Some more, some less, or whatever. But that means that you're inputting 2,000 calories of energy in your body. And if you're maintaining, your weight and your health or whatever, that means that that's how much work you're doing in a given day by just existing, by breathing. Okay, your body does work on itself by pulling air in and out of its lungs, by keeping your heart beating, by keeping blood flowing through your body, and really everything. If you slept 24 hours a day, you would still burn a lot of calories. Your body's still doing work. Your body needs to do work just to stay alive. Okay, so when we do work, we apply a force to move objects some distance. Okay, the equation for work, I'm not going to use that quite yet, but looks like this. Work is equal to force times distance. Now, work is a scalar quantity, and force is a vector quantity. And I guess usually this, would be a displacement. For most, it doesn't matter if we call it a distance or displacement, but if it is a displacement, both of these are vector quantities. But work, as well as energy, are scalar quantities. And when a force acts over some distance, that works to change the energy. So how much energy something changes, like when I throw that baseball, the amount of energy that I lost, or the amount of energy that the baseball gained, is equivalent to delta E, but it's also going to be equal to the force that I applied on it over that distance, over that displacement. So, and again, I can give energy in all kinds of forms: heat energy, thermal energy, sound energy, gravitational potential energy, kinetic energy, chemical potential energy. Okay? But energy, as we learn, can never be lost. It's only transferred. The total amount of energy in a closed system must remain constant. That holds true here. We just have to be able to identify where the energy goes. So that's just my very, very short intro on that. So the assignment that you're going to do is this is a short article. I'm going to pass out to you here. It says, Twinkie diet helps nutrition professor lose 27 pounds. Sounds kind of interesting. You're going to read this article. You're going to answer some questions. Dieting, Twinkies, doesn't really sound like normal physics stuff. But it is, and I want you guys to be able to connect that. So I'm just giving you the short, brief intro video to be able to connect those ideas of work and energy to something like this. So, guy ate junk food, lost weight. How did he wind up doing that? That's Twinkie is not a healthy food. So he did that by maintaining a certain calorie count. Okay, so let me ask you this. Okay, considering everything we know about energy, and I kind of already mentioned, without saying its name, the law of conservation of energy. But that's exactly what it is. The law of conservation of energy is that all energy must be accounted for. Anytime we have a conservation law, that means that everything is getting saved. It's not just deleting itself. So, say the professor normally eats 2,000 calories a day. What you eat is your input. Say he maintains his weight, nothing really changes, really simplifying things, that means that your output is also probably 2,000 calories. So if you're just maintaining input equals output, okay, no big deal. And again, I'm really, really simplifying a lot of nutritional things and a lot of fitness things here, but boiling it down to just simple physics, like most things in life, you can kind of really simplify it and make something very complicated like diet, nutrition, all these millions of dollars that people spend on diet plans and everything. Really all gets boiled down to brass tacks physics. So, 2,000 calories. So say he watches what he eats, which is exactly what happened. He just watched what he eat by eating junk food. Say he only has an input of 17,000 calories a day. His output is 2,000 calories. So that means that he's working at a deficit of 3,000 calories. He's still doing all the same stuff he normally does. Walks around, eats, breathes, sleeps, maybe even works out. Where's that extra 300 calories coming from? It's coming from his reserves. That's coming from the fat stored in his body. So, when your input is less than your output, you've got to tap into your reserves. Now, you can get 1,700 calories from fruits and veggies and lean meat and all that kind of stuff, or you could get 1,700 calories from Doritos and Twinkies and candy. Now, those aren't the best foods, but when you boil it down to just calories versus calories, calories are calories. And that's what the point he was trying to make in this article was. Now, in another hypothetical situation, you combine that, your input's less, and say you work out a little bit more. You hop on the treadmill for 30 minutes, burn an extra 300 calories. That means that you're working at a deficit of 600 calories. Hey, guess what? 600 calories a day that you are tapping into your fat reserves, that's where, if you want to lose weight, that's where that's going to come from. And the smaller you can make this number, and the larger you make that number, the bigger that differential is going to be. Now, I think if you know your body weight changes so much on a given day, water weight and just whatever time of day it is, but if you want to actually lose a pound of fat, I think calories to fat is like I want to say 30-some thousand calories. Translates to a pound of fat or something like that. That number might be off. I forget the exact number, but I don't know, maybe 12,000. I forget. But whatever it is, it would take a few days of working like this, maybe a week if I remember right, of working at a deficit of 600 to wind up actually losing a pound of fat. Now again, nutrition and fitness and all that kind of stuff, a million different things that all get factored into that. But really boiling it down, if you are not putting enough energy into your body, you're burning more energy than you're putting into it, that energy's got to be coming from somewhere, and that's coming from your reserves. I don't know why the light here is all acting funny. The adverse of that is going the opposite direction. Christmas break. I know I personally ate lots of Christmas cookies, and so your input probably went up. It's cold. You're not going outside a whole lot. You know, I obviously just had a kid, and your sleep schedule's weird, and you don't really do as much as you normally would. Certainly no time for working out, and so your output probably went down a little bit. So during Christmas time, you're probably working at a surplus of calories, which you don't want. Surplus means that you're probably going to gain weight, but things have a tendency to level out over time. So I'm going to cut myself off there. Read the article, answer the questions on the back, articles on the front, questions on the back. That's your homework for today. There'll be some more Professor Dave videos tomorrow, talking a little bit more about conservation of energy. And there'll be another short video of me explaining another short seat work assignment that talks about the law of conservation of mechanical energy. Mechanical energy is basically all forms that have to do with motion or position. So mechanical energy is the sum of KE and PE. But that'll be tomorrow. Then after that, the rest of your time will just be getting ready for exams next week. Have a pretty long exam review for you. Just printed off of quizzes. It's like 170 or so questions. But a lot of them are short questions, and it's just a really thorough review. Your exam is obviously not going to be that long, but it's going to be pretty long, and that should be a good review. So you get a couple days to work on that. There'll be a graded quizzes review that you do the quizzes in class. That'll go in the grade book with a curve, a shortened version of what the paper printout was. You'll do that either on Friday or Monday, and we'll do the exam. And then after exams week, I think it's like one more week and a half, and then I'll be back with you. But this should set you up for the first week back from break. Good luck, and I will talk to you guys later.